excited for all of you. And just a quick note, we'll be recording the talk portion of this meeting, but not the Q&A. So feel free to ask questions and discuss. And so today we have a very exciting topic from Mike Barker. Mike Barker is a planetary scientist at NASA Goddard Space Flight Center. He's a co-investigator on the Lunar Reconnaissance Orbiter Lunar Orbiter Laser Altimeter. His research focuses on developing new and improved maps of topography by fusing imaging and altimetry data and studying the light scattering properties of rocky bodies to learn about surface processes. And so Mike will talk to us about building a foundation model for lunar science and exploration. The floor is yours, Mike.
Okay, thanks a lot. Can you see my slide full screen?
Yep.
Okay, great. Yep, thanks a lot for the invitation to talk today. I'm going to be giving a kind of a brief overview of NASA's Lunar Foundation model, which we're developing in partnership with IBM, SETI, and the University of Alabama, Huntsville. And so I'm gonna focus on the science motivation, the data, and the challenges, rather than the model architecture itself, which is still kind of under development a bit. So with that in mind, though, some of you might be wondering what exactly is an AI foundation model. So it's really just a large machine learning model that's pre-trained on a vast amount of data. No labels are required, and using self-supervision techniques. And this enables it to perform a wide range of tasks. So in traditional machine learning, you build individual uh, custom custom built baseline models for different tasks, like mapping craters or classifying terrain, and you train them with large hand labeled data sets. In contrast, a foundation model is pre trained on these large amounts of unlabeled data with self supervision. And in the process, it's supposed to learn patterns and relationships in the data. And this allows it to be fine tuned to perform the same tasks without building an entirely new model from scratch, saving time and resources for the downstream user. So these foundation models are supposed to provide cross-modal, multi-scale, contextual reasoning quickly and efficiently, and they're supposed to generalize well to diverse tasks. For this effort, NASA's Planetary Science Division selected the moon due to its large dataset availability and immediate benefit to high priority science and exploration. At the moon, we're blessed with a large and diverse array of multimodal datasets, research topics, and AI ML applications. And here, the term modality can refer to text, audio, images, video, or other types of sensor data like accelerometers, bolometers, altimeters, or magnetometers. And when we talk about AI ML applications at the moon, we're talking about things like crater mapping, geologic mapping, searching for ice, hazard assessment, identifying and characterizing anomalous surface features, but also maybe more complex tasks like thermal modeling or illumination modeling or impact modeling, or morphological kind of crater age estimating. So, so this initial foundation model is supposed to be a basis for downstream machine learning models developed by the community that can power tools and approaches for advancing NASA's long-term lunar science and exploration goals. This Lunar Foundation model will incorporate state-of-the-art data sets and compute infrastructure. We're currently focusing uh, mostly on data acquired with the Lunar Reconnaissance Orbiter, LRO, supplemented with Kaguya and Grail data. And this provides a good starting point for future versions of the model when other missions and data sets can be incorporated. And there are a lot of other missions and data sets. But we've been limited by time and resources, so we had to pick kind of a core set of data that we think can provide a good kind of jumping off point for future development. And So we're partnering with IBM on the model development following successful foundation models that the same core IBM team uh, built for the Earth Science Division and the Heliophysics Division. Those foundation models were called, for Earth Science, Prithvi, and for Heliophysics, Surya. And so the architecture for the Lunar Foundation model will be roughly similar, based on IBM's TerraMind. And I'm not going to go into detail about that, but you can find this paper here by Jakubik et al. And last year. And so, yeah, I refer you to that for some more details. But there'll be some important modifications to kind of accommodate the certain aspects of the lunar data. And so the primary goals of this effort are to create a working example of a foundation model that can demonstrate the construction and scientific use of these things in planetary science. Um, and I think more broadly, NASA really wants to expand the community of AI practitioners across lunar and planetary science. These tools, not just foundation models, but ML and AI models in general, they're not going away. They're here to stay, and it behooves all of us, I think, to kind of get familiar with them and to learn how best to apply them in our research. And so finally, NASA wants to pilot the use of these things to lunar science and or lunar exploration applications. Okay, so the science motivation. So the initial model design considerations are guided by three broad science themes and goals that we kind of drew upon from various community documents, most notably the Planetary Science Decadal Survey. So the first theme is impact processes. This has the overall goal of understanding how the moon's surface characteristics and compositions have been modified by and recorded external processes. The second theme, volcanic history. This has a goal of determining the flux of lunar volcanism and its evolution through space and time. And the third theme focuses on polar volatiles, with the goal of determining the origin, composition, distribution, and effects of volatiles in the lunar polar regions. Now, these themes are certainly not exhaustive of all of the different science areas and exploration areas that the foundation model can be applied to, but they serve as a good kind of starting point, and illustration for future applications. And so many investigations in those three science themes employ broadly overlapping tasks, like identification of interesting or unusual features, characterization of such features, like measuring their dimensions, or the terrain slope or texture. Also contextualizing the features by studying their geologic setting, asking questions like, do they tend to occur in young or old terrain? Also classifying the features based on their characteristics and context. And these tasks also are certainly not exhaustive of all the things that a foundation model can be applied to. You could imagine more complex tasks like regression, and more physics-based tasks like impact modeling or thermal modeling. But these basic tasks can shed a lot of light on the origin and evolution of lunar surface processes, volcanism, and polar volatiles. So for science theme number one, impact processes, craters are one of the most important and distinguishing features of airless planetary bodies. So they represent a natural target for downstream applications. They can reveal important clues about the history of the moon, like the age of different terrains, the stratigraphy, chemical composition of the early lunar interior. The most common science tasks for studying craters are to identify them, characterize them, like measure their diameters and depths, contextualize them, classify them, and maybe even time order them based on chronology. And so these involve model tasks like feature detection, segmentation, and terrain classification, and morphological measurement, with expected science outputs. Obviously, crater centroids, diameters, but also depth to diameter ratios, and maybe morphology and degradation-based classification, and terrain unit segmentation. For science theme number two, the history of volcanism. Here, the bulk of basaltic volcanism on the moon is thought to have ended about 3 billion years ago, but certain surface features like these irregular mare patches and ring moat dome structures, they appear anomalously young when that challenges the long-standing view of lunar volcanic history. So their nature and origin is one of the biggest unresolved questions in lunar science. We'd like to be able to identify these features, any and all such features, characterize them, contextualize them, and classify them. Again, similar model tasks involving feature detection, segmentation, terrain classification, and morphological measurement, and similar kind of science outputs. And then for the third kind of science theme, looking at polar volatiles, the polar regions on the moon show evidence for hosting water ice and other volatiles, but their abundance and composition and distribution are very uncertain, but very important for understanding the history of water in the inner solar system and for resource mapping, for planning a kind of long-term human and robotic presence on the moon. So again, we're looking at science tasks like identification and characterization, contextualization, and classifying ice stability zones at the surface or in the near subsurface. And this involves similar model tasks, but also regression, looking at how different maps kind of relate to each other, and can predict ice prospectivity. Okay, so for the missions, as I said before, we're focusing on LRO, supplemented with data from GRAIL, which was this dual spacecraft mission about 15 years ago or so, that did radio Ka-band tracking between them and Earth to measure the lunar gravity field. And then the Japanese mission Selene, also called Kaguya. So I will say that there's a vast amount of other missions and data sets that can be included, but we had to pick kind of a core set of data sets, and this is what we chose. So for images, we have individual map projected images. These are globally distributed, high resolution, 1 meter per pixel, and medium resolution, roughly 100 meter per pixel images from the LRO narrow angle camera, the NAC, and the wide angle camera, the WAC. We also have global maps of surface and subsurface properties, ranging in resolution from 60 meters per pixel all the way up to 20 kilometers per pixel. And these are maps of things like topography, slope, aspect, roughness, also radar reflectivity, gravity, regolith temperature, rock abundance, thermal inertia, morphology, and multi-wavelength reflectance, and mineralogy. And then we also have local high-resolution topographic models. These are hundreds of local high-resolution NAC stereo digital terrain models distributed near globally. And these are really important because they provide kind of a complementary high-resolution view of the topography that the global data sets, global maps, don't have the resolution to capture. Some of the key challenges. Well, first, lighting conditions. The lunar surface can appear very different depending on the illumination geometry. There are pervasive shadows at low sun elevation and near the poles. So we care about these lighting conditions for pre-training and for using the model for downstream tasks. And so we're training it with metadata associated with every image that tells it the relative position of the sun. Also, co-registration. Uncertainties in spacecraft orbits, reconstruction, and instrument pointing can result in horizontal geolocation errors of the images that are tens of meters. And these can cause, for example, the same feature to appear at different places in NAC images. This will be more important in future model iterations. And it doesn't apply so much to the WAC images because they're much lower resolution than the NAC images. And to kind of get around this issue for now, we're focusing most of the LROC NAC observations on a special set of NAC, a special NAC data set called photometry sites that are specially curated sets of images co-registered by the LROC team. And they have co-registered images that are under different sun illumination geometries. So those are very important to the pre-training. Another key challenge is the variable resolution between the data sets. There's roughly 4 orders of magnitude difference in resolution between the highest resolution NAC images at 1 meter per pixel and the lowest resolution static maps at up to 20 kilometers per pixel. So we're kind of having to feed that information as well as metadata to the models to help it kind of learn how these features change in appearance given the different resolution. Also, map projections. We want to preserve shapes, so we need conformality, but we don't want to reinvent the wheel and kind of come up with some obscure mapping projection scheme ourselves. And so we gave a bit of thought to this, and we ended up deciding upon this USGS Lunar Transverse Mercator and Lunar Polar Stereographic System. This is documented, it's well documented, and it's GIS friendly. So you can read more about it here at this website, but yeah, it's a good way to kind of make sure that all of the map projection preserves all the shapes. And finally, for key challenges, lack of benchmark datasets. Planetary science lags Earth science when it comes to ML-ready benchmark datasets. Many papers have been published in planetary science describing AI ML applications, but their training and benchmark data are rarely published, especially for the moon. The situation I think might be a little bit better for Mars, but for the moon, there's still probably some work to do for us as a community as a whole. So in this project, we're transforming some key data sets from the literature into ML-ready benchmark data sets for our three main tasks, supporting those three main kind of science themes. These are the crater mapping, geologic mapping, and ice prospectivity. Okay, so just to wrap it up, we're developing NASA's first lunar foundation model to serve as a basis for downstream models developed by the community. And the model design is guided by science and exploration goals from community documents like the Planetary Decadal Survey. And a large and diverse array of modalities will enable new approaches to a range of science applications. Public release is expected by summer's end, and there's a workshop planned for later this year. And we'd love it if you take our quick survey to give us some feedback. And that's it. Thanks for listening.
Thank you so much, Mike. That was really nice.